Welcome! In this explainer, we're going to pull back the curtain on the internet itself. We're going to look at the fundamental blueprint for how pretty much all network communication works, the OSI model. It really is the hidden architecture that makes everything, from sending an email to streaming a movie, even possible.
You know, you click a link and a web page just appears. It feels like magic, right? But have you ever really stopped to think about what's happening under the hood? How does your request travel, maybe across the entire globe, and get the exact right information back to your specific browser tab? Well, it's not magic. It's a beautifully organized process.
To really get why this process is so important, we have to rewind the clock a little. Back in the early days of networking, we basically had a digital Tower of Babel. A computer from one company, say IBM, just couldn't communicate with a computer from another, like DEC. They spoke completely different languages, creating these isolated islands of technology.
So the solution was, well, it was brilliant in its simplicity. Create a universal standard, a common blueprint that any manufacturer could follow. So, back in the late 1970s, the International Organization for Standardization, that's the ISO, created what they called the Open Systems Interconnection Reference Model. It was designed from the ground up to be the universal translator for computers, making sure any system that followed the model could talk to any other.
Okay, so here's our game plan. First, we'll really dig into that communication problem. Then we'll unveil the blueprint for networks. After that, we're going to follow a piece of data on its incredible journey, starting with the applications you use, moving down to how it's transmitted, getting it onto the actual wire, and finally seeing how it's all put back together on the other side.
All right, section 1, the communication problem. Let's really get into why this blueprint was, and honestly still is, so absolutely necessary. Because in the world of networking, if you don't have a standard, you don't just get inconvenienced, you get total chaos. What everyone was searching for was interoperability.
Think about it like you're starting a company. You wouldn't just have one giant room where everybody does everything all at once. No, you'd create departments, a shipping department, an inventory department, a customer service team. Each one has a very specific job, and it relies on the others to do their jobs correctly. The OSI model does the exact same thing for network communication. It creates these departments or layers, making a massively complex process manageable, easier to build for, and way easier to fix when something breaks.
Now for section 2, where we get to look at the blueprint itself. So the OSI model is organized into 7 distinct layers, stacked one on top of the other. You can think of it as an assembly line, where each layer performs its specific task before passing its work on to the next one in a perfect sequence.
And here they are, the famous 7 layers. We start at the very top with layer 7, the application layer. This one's closest to you, the user. From there, your data starts its journey down through presentation, session, transport, network, data link, and it finally hits layer 1, the physical layer. We're talking the actual cables, the fiber optics, the radio waves that carry the signal. As data moves down this stack, each layer adds its own little wrapper of information, kind of like putting a letter into an envelope, then putting that envelope into a shipping box. This whole process is called encapsulation, and we'll see exactly why it's so important in a bit.
Okay, I know that's a lot to remember. So for decades, network engineers have used a classic little mnemonic to remember the layers in order from the bottom up. Please do not throw sausage pizza away. That's physical, data link, network, transport, session, presentation, and application. It's silly for sure, but trust me, it works.
Before we trace a packet's entire journey, let's just get a quick bird's eye view. A really helpful way to think about this is to group the layers into 2 main categories. The top 3, application, presentation, and session, are often called the upper layers. They're all about the software side of things, getting the data ready for its trip. The bottom 4, transport, network, data link, and physical, are the lower layers. They handle the nitty-gritty of how that data actually gets from point A to point B. So let's start our data's journey. Imagine you type a web address into your browser and you hit enter. That single action kicks off a whole process that starts right at the very top of the OSI model with these application layers. Layer 7, the application layer, is that interface. Now, it's important to note your browser itself isn't in this layer, but it uses protocols at this layer, like HTTP. This layer's job is to see that you want to talk to another computer, check if that computer is available, and make sure the resources are there to even make the connection. Your email client does the exact same thing when it uses protocols like SMTP to send mail.
Okay, next down is layer 6, the presentation layer. You can think of this as the network's universal translator. It takes the data from your application and makes sure it's in a standard format that any computer can understand. So, for example, it makes sure that character encoding like ASCII is understood by both sides so your text doesn't turn into a bunch of garbage characters. It also handles really crucial jobs like data compression to make files smaller and encryption to keep it all secure using things like SSL/TLS. That's what puts the S in HTTPS.
And next up is layer 5, the session layer. Think of this layer as the conversation manager or the dialogue controller. If you've got multiple tabs open in your browser, the session layer is what sets up, manages, and eventually ends the individual sessions for each one. This is literally what makes sure that the data from your online banking tab doesn't get all mixed up with the data from your cat video tab. It keeps all the conversations separate and organized.
So now we've reached the real heart of the journey. Our data has been formatted, it's been prepared. Now we hit layer 4, the transport layer. And this is where the heavy lifting of data transmission really begins. Its job is all about getting your data from your computer to the other computer, end to end, reliably. So what the transport layer does is it takes that big stream of data coming down from the upper layers and it chops it up into smaller, more manageable pieces called segments. Then it wraps each one of those segments in a header, kind of like addressing an envelope. This header has vital info like port numbers, which make sure the data gets to the right application on the other end. It's like delivering mail to the right department in a huge office building. This is a really key part of that whole encapsulation process. Now, here at Layer 4, there's a really important choice to be made between two flavors of transport. First, there's the connection-oriented method, TCP, which stands for Transmission Control Protocol. Think of this like sending a package with tracking and delivery confirmation. It's super reliable, but all that tracking and checking makes it a little bit slower. Then you have the connection-less method, UDP, or User Datagram Protocol. This is like sending a postcard. It's fast, there's very little overhead, but there's no guarantee it'll get there. So you use TCP for things like web browsing or file transfers, where every single bit has to be perfect. And you use UDP for things like online gaming or video calls, where speed is everything, and a dropped packet here or there is way less noticeable than lag.
So how does TCP make sure that connection is so reliable? It uses a really cool process known as the three-way handshake. It's like a polite negotiation. First, your computer sends a synchronized packet called a SYN packet. The server on the other end replies with a synchronized acknowledgement packet, or a SYN/ACK. Finally, your computer sends back one last acknowledgement packet, an ACK. And only after that three-step conversation is complete is the connection established and ready for data. And right here, you can see that little conversation visualized. The client on the left sends the initial SYN request. The server replies with the SYN/ACK, and the client finishes things off with that final ACK. It's the simple three-step dance that forms the foundation of every single reliable TCP connection on the internet. But what happens if the sending computer is like a race car, and the receiving computer is, well, not a race car? The sender could just flood the receiver with data, causing packets to get dropped. That's where something called flow control comes in. If the receiver's buffer, that's its temporary memory for incoming data, starts to get full, it can actually send a not ready signal back. It's basically a traffic light telling the sender stop. Once the receiver has caught up, it sends a ready signal, a green light, to get the data flowing again. And here's that traffic light in action. You can see the sender is just firing off segments, but the receiver's buffer is filling up. Once it's full, boom, it sends that not ready, stop signal, and the sender politely pauses. After the receiver has had a chance to process that data and clear some space, it sends the go signal, and the flow just picks right back up. It's a simple but really elegant solution that's crucial for preventing data loss in a world where network speeds are never perfectly matched. Now, imagine if the sender had to stop and wait for an acknowledgement for every single tiny segment it sent. Things would be painfully slow. To speed this all up, we use a technique called windowing. The window is just the amount of data the sender is allowed to transmit before it has to pause and wait for an acknowledgement from the other side. This visual makes the benefit of windowing so clear. Look at the top diagram. That's a window size of 1. The sender transmits a single segment, then it has to stop and wait for the acknowledgement to come all the way back before it can send the next one. It's this constant stop and go traffic jam. Now look at the bottom.
With a window size of 3, the sender can fire off 3 full segments, one after the other, before it has to pause for an acknowledgement. This creates a much smoother, continuous pipeline of data, and it dramatically speeds up the whole transfer.
All right, our data is all segmented up and ready for the big journey. Now we enter the lower layers, which are all about logistics. We're moving from managing just one single connection to figuring out the actual path across the entire internet. This is where we start talking about addresses and routing. So layer 3, the network layer, is basically the post office of the internet. It takes those segments from the transport layer and wraps them in another header, turning them into what we call packets. This new header contains the logical source and destination addresses, your familiar IP addresses. And the devices that operate at this layer are called routers. They're like the mail sorters of the internet, looking at that destination IP address and figuring out the best possible path for that packet to take to get where it's going.
And this here is a simplified look at the map that those routers use. It's called a routing table. It lists all the networks the router knows about, which physical port on the router to use to get there, and a metric, which is just a measurement of how far that network is, often counted in hops, or the number of routers it has to pass through. The router uses this map to make a split-second decision about where to forward your data next. Okay, so once the router sends your packet to the correct local network, layer 2, the data link layer, takes over for the final delivery. If the IP address is like a building's street address, the MAC address used at this layer is like the specific apartment number. This layer wraps the packet in one last header and trailer, turning it into a frame. It's all about that final hop, making sure the frame gets to the correct physical device on the local network, using its unique, built-in hardware address.
And we've finally reached the bottom. Layer 1, the physical layer, is where all those digital ones and zeros in our frame become actual physical phenomena. This layer doesn't care about addresses or packets. It cares about physics. It defines the electrical voltages for copper cables, the frequencies for your Wi-Fi, the pulses of light for fiber optics. This is where the data finally leaves the world of software and travels as a real signal across a wire or through the air.
So our data has made this incredible journey across the world as a physical signal, and it's arrived at the destination computer. So what happens now? Well, the entire process we just followed happens in reverse. It's time to unwrap the package and finally deliver the message.
This reverse process is called de-encapsulation. Remember how each layer on the way down added its own special wrapper? Well, now, on the way up, each layer reads the instructions on its wrapper and then strips it off. Layer 1 turns the physical signals back into bits. Layer 2 reads the frame header and passes the packet inside up to Layer 3. Layer 3 reads the packet header and passes the segment up to Layer 4. And this continues all the way to the top until the original, pristine data is delivered to the correct application, good as new.
So let's just recap why this whole layered model is so incredibly powerful. First, it breaks a hugely complex process into smaller, manageable parts. This makes troubleshooting way easier. It creates standards, which is why a Cisco router can talk perfectly fine to a Juniper router. It allows all different kinds of hardware and software to communicate seamlessly. And maybe most importantly, it means you can innovate in one layer without breaking all the others. You can invent Wi-Fi 7 at the physical layer, and your web browser at the application layer doesn't even need to know. It just works.
The OSI model has been the bedrock of networking for nearly half a century now. But as we move into a future of quantum computing, massive satellite internet constellations, and an Internet of Things connecting billions of devices, it raises a really fascinating question. What does the next blueprint for global communication need to account for? And what might it even look like? That's something to think about.